Here we go, reaction video number 29. This looks like it's a review day maybe or something, so it should be exciting. Here we go.
Okay, this is our test review for the work, power, and energy unit. And we're just going to go over this together. And I will also upload a copy of it, the filled-in version, so you have a copy.
Cool.
And I'll put a blank one. So follow along, whatever you need to do. Alright, so our equation for work is W equals force times distance times the cosine of any angle. So that angle, theta, in your equation is the angle between the force doing the work and the displacement.
Cool.
So in order for...
So this kind of structure is really, really useful for students, right? So it really helps sort of drive home not just the vocabulary, but how they all play together. And so to take the time to fill these out can really help sort of get it clear in the brain. Notice a couple of things that she did. So here, I think she said distance when she wrote this down, and then down here she wrote displacement. So I think that she's talking about scalar versus vector here, which is very, very cool. You have to keep that straight when we're talking about an angle. When she wrote this, she said, and the cosine of any angle, you know, and people go, oh, she can't possibly mean that. But come on, the next bullet point was the definition of the angle. So, you know, sometimes it's funny that students in like a geometry class will say, well, if you've got two things, the angle could be this one all the way around here. No, I meant this one. And luckily for a cosine, it doesn't matter, right? Could think the way the unit circle works. And so that's really interesting. As she goes down here, what I'm expecting to hear is, you know, sort of connections to the way they've run into it in class, not rather than just like a robot reading this.
Work to be done on an object. A force must be exerted, and the object must be moved.
Yeah. And so that bullet point is so fascinating, right? Because you can get tired pushing on a wall that never moves, right? And so I am fascinated by this idea of energy, work, getting tired, because when you just hold your arm out, that can get tiring. And it's a really interesting question, right? Like, you're not moving it, you're not doing any work on your hand, and if I was a robot, I could just clamp this, I could clamp that shut, and I'd be good to go. And would the joint get mechanically tired, right? So there's super subtle things going on when there's very tiny little motions in my arm that are not, reversible, right? And so I think that it's really subtle, this third bullet point here, that must be moved. And of course the follow-up here, which I'm guessing she's going to say, displacement again here cannot be 90 degrees. So that's like a car going along and being pelted from the side and not being moved, right? It seems like you could get tired trying to get something to turn, and it's just not turning, right? So this idea of super massive things not changing when it feels like you're pushing really hard, I think it can be subtle in classes like this.
And the angle between the force and the displacement.
Yep. Love the consistency.
Cannot be 90 degrees. The reason for that is the cosine of 90 degrees equals 0.
Cool. That extra business right there. Just
also,
that extra little business is great. So when she added, the one thing she didn't write was the reason for that, right? These audio cues, these video cues that we can use in addition to a handout like this are so powerful.
Remember, have your calculators in degree mode.
Yeah.
If you're in radian mode, it'll give you the wrong answers.
For
All right,
sure.
so power is defined as the rate at which work is done or the rate at which energy is consumed. So our metric or SI unit for power is the watt, where 1 watt equals 1 joule per second. So every second, 1 joule of it.
And it's great, right? With all of this stuff in there, you can say, okay, well, hang on a second. Work is work is this crazy thing, and then the per second, I get the per second thing. Aha, well, this must be the units of work, and so that must be newtons meters, right? So it's all kind of there for the students to help work out.
Energy will pass through. You can calculate net work by calculating the work done by the net force, or by calculating the work done by all the forces and adding them together.
So that's a really, really intriguing concept, and it's lucky that that the universe works this way. The first one, calculate the work done by the net force. Like, you're an object, you're being buffeted by lots and lots of things, but ultimately you feel like you're being, overall being pushed in that direction. Okay, well then figure out how far you went and how hard you were being pushed, and that's the work done. This second way, right, mathematically, it's straightforward, like, duh, of course, you can just do it all, separately and then add versus adding and then multiplying. So from a mathematical perspective, it's a pretty straightforward concept, but think about it, right? You're not actually letting each force do its one thing at a time. Well, let me see what this force is doing as I move that way. Let me see what this force is doing while I move that way. Those things aren't happening individually, and yet you can pretend that they all do it all on their own and then add it all up. And that's just such a useful concept that we use all the time.
According to our kinetic energy theorem, the net work done on an object is equal to the change in the object's kinetic energy.
Awesome.
All right. We did not cover positive and negative work, so we're not going to do that one.
That's awesome. That's super awesome, right? So, again, if this were handed out to students and she had forgotten to do that, forgotten to cross that one off, you could just imagine, oh my God, I don't know what the heck this is. I need to flip through my book and I don't understand, but I'm just going to fill this out. For her to be able to say in the video, look, we didn't get there. We're not talking about it. We're just going to let it be. Is so useful. And frankly, I think even better than a handout with these things crossed out.
3 types of mechanical energy that we've talked about in this particular unit is we have had potential gravitational energy, kinetic energy, and potential elastic energy. Energy in our universe cannot be created or destroyed.
In our
universe. Moved around. The mechanical energy of the system is conserved, so long as only conservative forces do work.
So, she doesn't have an adjective in front of this word energy. So, I don't understand dark energy. I just don't get it, right? So as the universe expands, every cubic meter, centimeter, millimeter, whatever you want to do, has the same amount of dark energy into it. It's what helps explain why, the expansion of the universe is happening the way it is. Doesn't that mean that energy is being created? All right, you astro people, help me out, because my question for you is, does she have to put an adjective in front of this?
2 conservative forces we've covered are gravity.
Oh, I like this.
And we've also covered elastic forces. When friction does...
It's interesting. I don't tend to use the word elastic. I don't know. I'm constantly talking about spring forces or Hooke's law forces. But elastic, what's interesting about elastic in common everyday usage is that it can stretch, but it's usually not a compressive force. I don't know. Maybe I'm just thinking about elastic bands or something. So if you take an elastic band and try to compress it, I guess it pushes back, but it usually sort of wobbles. But definitely if you stretch it, it pulls back on you. So it's one-dimensional. And so I tend to use the spring concept. Springs usually make sense. So if you compress them, they push back. If you stretch them, they pull back. So it's an interesting adjective. Of course, there's a scientific definition of elastic, which probably is the same as Hooke's law. So interesting.
Does work. Your mechanical energy is converted into heat, so thermal energy.
Cool. And again, remember, there's no adjective in front of this one here. So that would be, you'd have to say that there's the sum of mechanical and thermal so far that they talked about. Ooh, interesting. What's going on here?
All right. So if we have a child slides 2 meters down the slide.
Well, she's really good at this.
If they instead go
Whoa.
twice as far,
Man, I mean, she's doing multiple things at once here. I mean, teachers are awesome. Come on, she's moving the page, she's adjusting her software, she's keeping the thought going, she's trying to keep the students engaged. It's amazing. It's just amazing.
your work done by gravity is going to increase because you're moving twice as far,
Oh, I really like
and by
this.
a factor of 2 because we doubled.
So, just a quick note. So, I go to the new faculty workshop for physics and astronomy, folks, twice a year for years and years and years. I go to these things, and I have my particular role that I play there, but I love listening to experts talk about sort of classroom management and ideas you can use in the classroom. And this idea, this fill-in-the-blank idea, is something that really, really works. So imagine you're in class, and you say, if the child slides twice as far, the work done by gravity increases by a factor of 2, right? And if you can really structure these right, it's amazing how well it works. And people say all the time, oh, well, that's an elementary school thing to do. I'm not sure if I like doing it in college level, let's say, because this is typically an audience of college teachers. And what's fascinating is they are doing it. Literally, they're doing it, and it's working great. And so I'm sold. I am sold. And so, I think that these fill-in-the-blank worksheets don't always work because typically when I see it work the best, it's when the answer is almost obvious. So the example I've seen the most often from my good friend Ed Prather is about solar system, right? The moon orbits around the... right, and the Earth orbits around the... right, so you don't need to be providing these increase, decreases, does not change words. And so I think that I'm really, really intrigued by fill-in-the-blanks. Maybe it harkens way back to those Mad Libs. I remember I started doing those in about, 5th grade or something, back when I didn't know what an adverb was. All right, very cool.
Our distance. If your angle between your force and your displacement increases from 5 to 30, your work done on a force will decrease.
Stupid cosine. Why would we
Because
be in
you're
love with a
pulling
trigonometric function that
less
decreases when
parallel
the thing
with
increases?
the direction the object is
Dumb.
moving. So, if you double the speed of your object, you are going to increase
Oh, this
your
sounds
kinetic
good.
energy by a factor of, you're doubling your speed, but speed is squared, so it's by a factor of 4.
Love it. That's
If you're
really cool.
doubling your height, you are increasing.
So one question that I have for you guys is, I do this kind of thing a lot where I'm using easy numbers to be able to do it. I'll double, just like exactly what she's doing here. But what I've noticed is that 2 squared equals 4. I think, oh, it's obvious. Hey, you just square it, you get to 4. But there's a bunch of situations where there's factors of 2 in the calculation or in the whatever. And so sometimes I feel like my students are being crossed up here because they say, well, it's just 2 times 2. It's 2 times 2 equals 4, as opposed to the squaring. And so I actually have found that on occasion saying tripling instead of doubling can really help with that, because it turns out we have way less factors of 3 in our various equations than we have extra factors of 2 floating around. So I don't know, something to think about, I guess. Doubling things is easier to visualize. Like, tripling takes a little bit more thought, but I wonder, that's my question for the audience here, how important is it for them to understand this is a power connection as opposed to just a 2 times connection?
Your gravitational potential energy by a factor of 2.
Cool.
Okay. If we have an object 5 meters above the Earth's surface has 50 joules of gravitational potential energy. If we take that same object to the moon and hold it the same distance above the surface, you would have less gravitational potential energy because the moon has less gravity.
Yeah, love it. So there's this extra piece that she needed to add. This moon has less gravity that she needed to write.
All right. So if we
Otherwise, students might not remember that. I mean, I think that it's sort of drilled into physics students that, the moon has less gravity. But to explicitly say it like that is, I think, super important.
We've compressed the spring 0.1 meters. If this compression is doubled to 0.2 meters, the elastic potential will increase. We are storing more energy in the spring by a factor of 2, but distance is squared.
Ha ha ha.
So
Love it.
by a factor of 2 squared or 4.
Yep. Love it. All right, I'm going to stop right there. I think this is a really, really great review. I'm trying to imagine, students doing several things. Having the sheet without her video, having the sheet while watching the video, and then filling the sheet out themselves afterwards, right? All of those are useful. That last one, of course, is very often the advice we give to students. We say, hey, after class, you should go back to at home or, during homework or back to your dorm room if it's in college, whatever. And we say, you should, rewrite your notes. Well, this is a great example. Imagine if you had sat here and listened to this and nodded your head, oh yeah, and then faced a blank screen or a blank sheet of paper and had to do it yourself. You're going to find where your pauses are. And I always say to my students, pay attention to when you're pausing as you're thinking about studying for an exam. Really, really great. Loved the clarifications that she added. I'm intrigued by this idea of dark energy, which has nothing to do with what she's up to, but it's just a separate question that I have. Really great. So have a great day, everybody. And remember, physics teachers are awesome.